Imagine walking into a room where every wall, every machine, every worker, and almost every object around you is covered in paint. Now think about this. The global paint industry produces tens of billions of liters every single year, enough to coat entire cities over and over again. Most people see paint as nothing more than color inside a can. But here's what nobody tells you. That smooth liquid hiding on a hardware store shelf is actually one of the most carefully engineered products on Earth. The journey begins thousands of kilometers away from the factory floor. It starts deep underground in giant mineral mines, inside chemical plants, and even in forests where natural ingredients are harvested. Every bucket of paint contains materials that may have traveled farther than many people do in a lifetime. And before this documentary ends, you'll see how rocks, chemicals, and science combine to create the colors that surround your everyday life. What happens next surprised even experienced engineers. The most expensive ingredient inside many paints isn't the color at all. In some premium products, a single ingredient can cost hundreds of times more than the raw minerals surrounding it. So where does paint really come from? Let's follow the trail all the way back to the source. Most modern paint begins with titanium dioxide, the brilliant white pigment responsible for brightness and opacity. Nearly 60% of all pigments used worldwide rely on this remarkable mineral. Large quantities originate from mineral sands mined in countries such as Australia, South Africa, Canada, and Mozambique. The raw ore may contain over 95% titanium-bearing minerals before refining begins. The mining process looks more like a giant earth-moving operation than paint production. Enormous excavators remove thousands of tons of sand every day. Conveyor systems stretch across the landscape like mechanical rivers. Workers monitor screens while giant separation plants extract valuable minerals from ordinary-looking soil. Most people never think about this when opening a fresh can of paint. Color pigments come from many different sources. Iron oxides create reds, yellows, and browns. Carbon black delivers deep black shades. Specialized organic pigments create vivid blues, greens, and bright reds that almost seem to glow under sunlight. Some of these pigments require highly controlled chemical synthesis before they ever reach a paint factory. But pigments alone cannot become paint. They need binders. Acrylic resins, alkyd resins, and other polymers act like microscopic glue. These materials often come from large petrochemical facilities where raw hydrocarbons undergo complex refining and polymerization processes. A single shipment may travel more than 5,000 kilometers before reaching its destination. Water-based paints also depend on carefully purified water. That sounds simple until you realize that impurities measured in parts per million can affect color consistency and drying performance. Manufacturers continuously test water quality because even tiny variations can change the final product. Precision begins long before mixing starts. Then come the additives. These ingredients may represent only a small fraction of the formula, but they control everything from drying speed to mold resistance and surface texture. Some additives cost thousands of dollars per ton. Without them, paint could separate, crack, foam, or lose color long before reaching your wall. The environmental footprint of these materials remains a growing challenge. Mining operations move massive volumes of earth. Chemical production consumes significant energy. Transportation networks burn fuel across oceans, railways, and highways. Modern manufacturers now invest heavily in recycling systems, low-emission technologies, and renewable raw materials to reduce that impact. Finally, after traveling through mines, refineries, laboratories, ports, trucks, and warehouses, the ingredients arrive at the paint factory. Thousands of tons of raw materials wait inside towering silos and storage tanks. Everything has led to this moment, because what happens next transforms separate ingredients into one of the most versatile products humanity has ever created. Now the real transformation begins. Inside the factory, computerized systems weigh every ingredient with astonishing precision. Some premium formulations allow less than 1% variation between batches. Operators monitor digital screens while automated feeders transfer pigments, binders, additives, and water into giant stainless steel mixing vessels. The process looks calm from the outside, but thousands of chemical interactions are about to begin. The first stage is known as premixing. Giant agitators begin rotating at roughly 200 to 500 revolutions per minute, pulling powders and liquids together into a thick slurry. You can hear the deep mechanical hum echoing through the building as pigments disappear beneath swirling liquid. The smell of fresh chemicals fills the air while sensors continuously measure viscosity and temperature. But here's where things become extraordinary. Even after mixing, pigment particles remain too large to produce smooth paint. Manufacturers must break those particles into microscopic sizes. To accomplish this, the mixture enters high-speed dispersers spinning between 1,000 and 1,800 revolutions per minute. The force generated inside these machines can transform rough pigment clusters into particles measured in microns. As the disperser accelerates, temperatures can climb toward 40 degrees Celsius to 60 degrees Celsius, or 104 degrees Fahrenheit to 140 degrees Fahrenheit. Cooling jackets surrounding the tanks remove excess heat before it damages sensitive ingredients. Imagine standing nearby. You would hear a roaring mechanical sound similar to a jet engine in the distance while the liquid forms a spinning vortex beneath the blade. What happens next surprised even experienced engineers. Many paints undergo a second grinding stage inside bead mills. Tiny ceramic or glass beads collide with pigment particles thousands of times every second. Pressure inside the system may reach several bar, while microscopic impacts continue for 30 minutes or even several hours. This step determines whether paint appears silky smooth or disappointingly rough. Once grinding finishes, technicians test particle size distribution. Modern decorative paints often target pigment sizes below 10 microns. That's smaller than the width of a human hair by a factor of several times. If the particles remain too large, the batch returns for additional processing. Nothing moves forward until the numbers match the specification. The concentrated pigment paste now enters the letdown stage. Additional binders, additives, and water flow into the mixture through automated pipelines. Agitators continue spinning at lower speeds, often between 100 and 300 revolutions per minute, creating a perfectly uniform liquid. Slowly, the thick paste begins to resemble the paint you recognize from everyday life. The concentrated pigment paste now enters the letdown stage. Additional binders, additives, and water flow into the mixture through automated pipelines. Agitators continue spinning at lower speeds, often between 100 and 300 revolutions per minute, creating a perfectly uniform liquid. Slowly, the thick paste begins to resemble the paint you recognize from everyday life. Next comes filtration. The paint passes through precision filters that capture unwanted particles, contaminants, and debris. Some systems remove material larger than 50 microns. The flow moves steadily through stainless steel housings while pressure sensors monitor every second of the operation. One tiny contaminant could ruin thousands of liters of finished product. Now comes one of the most satisfying moments in the factory. Freshly finished paint flows through filling lines at astonishing speed. Automated machines fill hundreds or even thousands of containers every hour. Nozzles descend, paint pours smoothly into cans, lids snap into place, and conveyor belts carry each container toward labeling stations. Robotic palletizers stack completed cans with remarkable precision. Laser-guided systems arrange layer after layer onto shipping pallets while stretch-wrap machines secure the load for transportation. The rhythm of moving conveyors, robotic arms, and packaging equipment creates a synchronized industrial ballet that never seems to stop. But before a single can leave the factory, one final challenge remains. The paint may look perfect. It may flow perfectly. It may even match the target color perfectly. Yet hidden defects can still destroy performance months or years later. And that brings us to the most demanding part of the entire journey, proving that every batch deserves to reach the customer. Every can of paint now enters a world of inspections, measurements, and tests so strict that even tiny imperfections can trigger rejection. Most people imagine quality control as a quick visual check. The reality looks more like a high-tech science laboratory. Here, computers, sensors, robots, and skilled technicians work together to ensure that every drop performs exactly as promised. The first challenge is color accuracy. Spectrophotometers shine controlled light onto paint samples and measure the reflected wavelengths with extraordinary precision. These instruments can detect color differences invisible to the human eye. A variation smaller than 1 delta E unit may still trigger investigation because customers expect identical color whether they buy paint today or 6 months from now. Next comes viscosity testing. Engineers need to know exactly how the paint flows. Too thick, and customers struggle to spread it evenly. Too thin, and it may drip down walls before drying. Automated instruments measure flow characteristics within narrow tolerances, often allowing only tiny deviations between batches. But here's what nobody tells you. Paint must survive conditions far harsher than most homes ever experience. Specialized chambers expose samples to intense ultraviolet light, moisture, heat, and freezing temperatures. Some tests simulate years of outdoor weather within just a few weeks. What happens inside these chambers predicts how paint will perform long after it leaves the factory. Engineers also test adhesion strength. Fresh paint coats metal, wood, concrete, and drywall panels before undergoing pull-off tests and scratch resistance evaluations. Some coatings must withstand forces measured in megapascals before failure occurs. The goal isn't simply making paint look good. The goal is making sure it stays where it belongs. Now automation takes over. AI-powered vision systems inspect containers moving along conveyor belts at high speed. Cameras capture thousands of images every minute while machine learning software searches for dents, labeling errors, leaks, and filling defects. Some systems detect flaws measured in fractions of a millimeter. The human eye simply cannot match that speed. Laser measurement systems verify container dimensions and lid alignment. Sensors track filling accuracy down to extremely small weight differences. If a can falls outside specification, automated gates immediately remove it from the production line. In some factories, rejection rates remain below 1%, proving just how consistent modern manufacturing has become. And this is where human expertise still beats machines. Experienced color specialists often perform final visual evaluations under carefully controlled lighting conditions. They can notice subtle visual characteristics that instruments sometimes interpret differently. Decades of experience allow them to recognize problems before they become expensive mistakes. Even in an age of automation, human judgment remains indispensable. International standards add another layer of scrutiny. Manufacturers routinely work toward certifications such as ISO quality management systems and environmental compliance standards. Every batch generates records, measurements, and traceability data. If a problem appears anywhere in the supply chain, engineers can often track it back to a specific production run within minutes. Think about this. Before a single can reaches a store shelf, it may undergo dozens of separate inspections and tests. Temperature, color, gloss, durability, density, drying performance, chemical stability, and packaging integrity all face scrutiny. Every successful result increases confidence that the product will perform exactly as expected. Yet one mystery remains. After all this engineering, all this chemistry, and all this testing, just how enormous is the paint industry itself? The answer involves billions of liters, hundreds of billions of dollars, and a global network so vast that it touches nearly every building on Earth. And the numbers are far more shocking than most people realize. The paint industry is far larger than most people imagine. Every year, manufacturers around the world produce well over 50 billion liters of paint and coatings. If you poured that volume into standard household paint cans, the line could stretch across entire countries. From homes and skyscrapers to ships, bridges, aircraft, and factories, paint protects and transforms nearly every corner of modern civilization. The global paint and coatings market now generates hundreds of billions of dollars in economic activity. Every container sold represents a chain of miners, chemists, engineers, factory operators, truck drivers, warehouse teams, laboratory technicians, retailers, and construction workers. What looks like a simple can on a store shelf actually supports one of the world's most interconnected manufacturing ecosystems. Today, China leads global paint production with roughly 1/3 of worldwide output. The United States follows as another major producer, while India, Germany, and Japan remain among the most influential manufacturing nations in the sector. Together, these countries account for a substantial share of global production. Their factories operate around the clock to meet demand from rapidly growing industries and expanding cities. And the workforce behind this industry is enormous. Millions of people worldwide participate directly or indirectly in paint and coatings production. Their efforts keep buildings protected from weather, vehicles resistant to corrosion, and infrastructure functioning for decades longer than it otherwise could. Most people never see these workers, yet their impact surrounds us every day. The story of paint stretches back thousands of years. Ancient civilizations created pigments from charcoal, clay, minerals, and natural dyes. Egyptians decorated tombs with colorful coatings. Romans improved formulations for architecture. But the Industrial Revolution changed everything. Mechanized production transformed paint from a luxury product into something available to millions. Over the last 50 years, the industry has undergone a remarkable transformation. Solvent-heavy formulations gradually gave way to cleaner water-based technologies. Automation replaced many manual processes. Computer-controlled color matching achieved levels of consistency once thought impossible. Paint became safer, more durable, and far more environmentally responsible than previous generations could have imagined. Did you know that some advanced industrial coatings can protect steel structures for more than 20 years before major maintenance becomes necessary? In harsh environments, that protection saves enormous amounts of money and resources. Without specialized coatings, corrosion would destroy critical infrastructure at a much faster rate. Did you know that some research laboratories are developing self-healing coatings capable of repairing minor scratches automatically? Imagine a future where damaged surfaces restore themselves without repainting. What sounds like science fiction today is already moving closer to commercial reality. Did you know that some research laboratories are developing self-healing coatings capable of repairing minor scratches automatically? Imagine a future where damaged surfaces restore themselves without repainting. What sounds like science fiction today is already moving closer to commercial reality. Looking ahead, experts expect continued growth driven by urbanization, infrastructure expansion, renewable energy projects, and advanced manufacturing. Smart coatings may one day monitor structural health, improve energy efficiency, or even interact with digital systems. The future of paint could involve far more than simply adding color to a surface. From mineral mines and chemical plants to automated factories and advanced laboratories, you've followed one of the most fascinating manufacturing journeys on Earth. What began as raw materials hidden beneath the ground became a carefully engineered product capable of protecting, decorating, and preserving the world around us. Every stage demanded precision, expertise, and technology working together at an extraordinary scale. Most people never think about the science hiding inside a can of paint. Yet behind every brush stroke lies a story of global supply chains, advanced chemistry, powerful machinery, and relentless quality control. The next time you see a freshly painted wall, a colorful vehicle, or a towering bridge protected from corrosion, you'll know the remarkable journey that made it possible. The next time you hold one of these in your hands, remember, it didn't just appear. It was born from the earth, shaped by fire, perfected by technology, and approved by the strictest standards in the world. That's not just a product. That's a masterpiece of human engineering. If you want to go deeper into the hidden world of manufacturing, tell us in the comments what product you'd like to explore next. Like this video, subscribe to the channel, and we'll see you inside the next factory.